ladies and gentlemen, on behalf of the chair of Geoscience Remote Sensing, IEEE, and Taipei Tech, we are honored to announce by TSU as today's host. We would like to introduce today's speaker, Professor Ku. Professor Ku is currently a full professor of Multimedia University in the Faculty of Engineering and Technology, Malaysia. His research interests include remote sensing technology, signal processing, data analysis, and embedded system. He has published more than 100 papers in journal, international conference, 4 books, and 12 patents. He is the recipient of Young Engineer Award by Institute of Engineers Malaysia in 2004. Professor Ku currently chairman of Center for Remote Sensing and Surveillance Technology, CRSST, in Multimedia University. Vice Chair of IEEE Geoscience Remote Sensing Society Chapter, Malaysia Section, a registered professional engineer and a fellow of the Ancient Academy of Engineering and Technology, and a senior member of IEEE. Professor Ku is also the founder of a spin-off company from the University Research Center. The company, iRadar, was incorporated in 2011 with primary focus on provide smart sensing and AI solution for precision farming and more. Now, we welcome Professor Ku to deliver his talk titled Introduction to Synthetic Aperture Radar, or SAR. Let's give Professor Ku a big applause. Thank you.
Thank you. Thank you, Professor Chan. Good morning to all of you. First of all, I would like to thank the organizer to organize this seminar. Okay, I'm very happy to share with you some of the things that I know. Okay, especially here today, I understand that this talk, okay, there are quite a number of postgrad students in this particular area. So I would like to share with you an overview of synthetic aperture radar. So this is 1 hour talk. So I would try to give you an overview of the synthetic aperture radar, and I think what I'm going to deliver here is actually mostly for beginners. Okay, I assume you have background in engineering. If you are in electronics and electrical, that would be best. Okay, but if it's not, it doesn't matter. I think most of the thing it should be simple enough for everyone to follow. I also will give also some design idea how to do a radar system. Okay, so let's begin our talk. So today I'm going to break the talk into 4 parts. One is an introduction to radar. Okay, before we can understand or try to know about synthetic aperture radar, first is we have to know about radar. Okay, then after that we are going to look at what is SAR, and then how are we going to process a SAR image, and lastly is just to share with you some of the ideas of if you want to build a SAR system. Okay, so SAR system is actually under it can be used for military purposes as well as for civilian application. So here, I think mostly we focus on remote sensing application. Okay, so when we talk about remote sensing application, there are many ways for us to classify the remote sensing system. We can use a platform to differentiate between one to another. For example, they have a spaceborne system, airborne, and also ground-based system. For airborne system nowadays, we have drone, we have UAV, so we also classify them in terms of high altitude or low altitude airborne system. Basically, why we want to have this kind of different types of remote sensing system, it is for us to have a more consistent, timely, and large-scale monitoring of our Earth environment. Like for example, SAR, we can mount the SAR on spaceborne. We also can have a ground-based SAR as well as an airborne SAR system. And each of these, they look at the targets of interest at a different altitude, and therefore they will have a different type of information that we can monitor. So under this remote sensing sensors category, largely we can actually categorize them in terms of say the way we send or transmit a signal. Okay, it could be under active or passive system. Active here means it will have its own transmitter. That means it has its own source of illumination. Passive group, normally they will need to depend on the sunlight. So if there's a sunlight, then you can see. For example, say if you use camera. Okay, so in the daytime there's enough sunlight, then we can see a lot of color spectrum. But nighttime maybe we can't see that. Okay, there's another group called active group, whereby they carry its own transmitter. We generate our own signal and to send the signal out. Therefore, that group, it will be more suitable for day and night monitoring. So synthetic aperture radar is one of these under the category of active, and also is under a category of imaging. Okay? For radar system, most of the conventional radar system we call as a non-imaging system. Okay? But synthetic aperture radar is a high resolution imaging radar. So first, let us just to review what is radar. Okay, radar stands for radio detection and ranging. It's old terms used in late 30s. So radar is actually an object detection system, and it's a remote sensing system where there is no physical contact to the object. So radar is active, as we mentioned, and then it uses radio wave. So when we talk about radio wave typically it has a wavelength between 3 kilohertz or 100 kilometer to 1 millimeter, okay? Or in frequency is 3 kilohertz to 30 kilohertz. For very low frequency, like for example, VLF, LF, and MF, so all this very low frequency, the wavelength is actually very long. Okay? For example, more than 1 kilometer. And this is actually not suitable or not that suitable for radar system, because longer wavelength, meaning we need to have a very big antenna or large antenna aperture. So normally for radar system, we work in the range of higher frequency, whereby the wavelength is actually in the range of centimeter to millimeter. Okay, so in the range of 300 megahertz to 300 gigahertz, this is actually the range of the operation of radar. Okay, and more popular band is actually from 1 gigahertz to 18 gigahertz. So these are the popular bands for remote sensing radar system. So why we need to use radar is because radar is all weather, as I mentioned. Okay, it can operate day and night, and then will complement optical information. If you look at the wavelength, the absorption band of radar in the microwave region, so from 100 centimeter to 1 centimeter, this is kind of an optimum window for microwave radar for remote sensing application, which is about L band to Ku band. Okay? If it is after K band and onwards, the absorption of the atmospheric effect is actually very high, and therefore sometimes it will not suitable for long distance remote sensing application. So in principle, what kind of information can the radar obtain? Okay, basically for radar system, we can get 3 basic information. First is the distance. Okay? From a radar, because we send a signal, and then a portion of the signal will be reflected back to the receiver. So by checking the time delay from the signal sent out to the object and calculate the time back to the system, we will be able to know the distance, okay? The distance between the antenna and the target. So distance is possible, okay, by using radar. The other thing is velocity. If the target is moving, we can actually send, say, for example, a continuous wave, and then we look at the Doppler shift, and based on the Doppler shift frequency, we can also know the velocity of the moving target. Okay? The third thing is about backscattering coefficient. Okay? This is actually the property related to the target. So by looking at the power and also the relationship between the equal wavelength and also the transmitted wave, we will be able to calculate or to understand some of the characteristic of the targets. Okay, so that characteristic of the target is actually contained inside this backscatter coefficient, or we call it as a sigma number. So basically, a radar system can provide these three different types of information. Let us start with a very simple radar, continuous wave radar. Okay? So continuous wave radar mainly is used to measure the speed or the velocity. Okay? So basically, to design a continuous wave radar, first is we need to have an oscillator, a good oscillator that can generate a sinusoidal wave. And this sinusoidal wave, when you hit the target through antenna, and we send out through antenna, hit the targets, and then if the target is moving, there will be a Doppler shift effect. Okay? So by measuring the Doppler shift, okay, we will be able to detect, okay, because the Doppler shift is related to the velocity. So by measuring a Doppler shift, we can detect the velocity or the speed of the moving target. So another type of radar is called pulse radar. In pulse radar system, we send a pulse, okay, a very short pulse, and then we try to wait for the return. So by measuring the time difference between the transmit and also the receive pulse, we will be able to get back the distance information, because the two times of the distance between the antenna and the target divided by the speed of light will get the time delay. So by having a simple calculation, we will be able to get the range measurement. Okay, and in order for us to get a very good resolution for pulse radar, we need to have a very narrow pulse. Okay, because otherwise, from one echo to another echo, if there overlaps, we will not be able to separate them in the time domain. Okay. However, if you want to have a very narrow pulse, basically it means we have to decrease the average power, or otherwise we have to send a very sharp or very high peak power. Okay, and if that is the case, okay, to realize the very high power radar system, you need a very good amplifier, and that is actually also very expensive. Another way to do that is actually we use a modulation scheme. Okay, so that comes what we call as a FMCW radar. So FMCW radar, it can measure range, but it's not a pulse type. It's actually using a frequency, a continuous wave, and modulate the frequency so that we can measure the range based on the frequency modulation content. Okay, so basically this is similar to the CW radar, but then we need a sweep generator, okay, to sweep the frequency versus time. Okay, if you look at the signal, is still a sinusoidal signal, but then the frequency is a function of time. So let's say, for example, you have a linear FM. We send a up chirp followed by a down chirp. Okay, this is a triangular modulation. The signal will be when it goes to a very high frequency. Okay, the signal is higher in frequency, and then slowly, okay, there's a linearly reduced, and at the lowest point, then it will increase again. So by having this kind of modulation scheme, if we compare the transmit signal with the receive signal, then assuming that we have a mixer that can down convert or mix the transmit and the receive, then we will be able to get the difference between the frequency at every instant of time. And by looking at the relationship between the transmit and the receive, we will be able to calculate the range, okay, by having this triangular formulation. Okay, so the range is actually a related or function of the intermediate frequency, okay, intermediate frequency, and then over the bandwidth and also the modulating frequency. Okay, so all these parameters, for example, the bandwidth we can set when we do the radar design, and FM is also a period that we can set, okay, when we generate the FMCW system. So the things that we are going to measure is the IF frequency. So by having the frequency, we look at the frequency component and we relate that to the range. Okay? So this is actually a popular technique nowadays for us to measure, to get a high resolution radar by using a frequency modulation scheme. And you look at this range, the resolution of the range is actually depending on the inversely proportional to the bandwidth. So if we want to have a very high resolution range, then we can have a very high bandwidth system. This is one of the examples. Okay, I show you some of this sample code here. Okay, the linear FM system is one of the popular scheme now that we can generate, okay, and use in synthetic virtual radar. Okay, so basically we sweep the frequency from one time to say t equals to 0 to t equals to t capital T0. Okay, and the frequency is a function of the time. Okay, and if you look at the instantaneous phase, is actually a function of time squared. So therefore, the baseband signal is actually a function of t squared. Okay, so the signal, it looks something like this. Okay, whereby is a linear chirp. Okay, we call it as a chirp, and the bandwidth is related to how much frequency sweep that you can allow. Okay? Typically, say for example, you want to sweep from 1 gigahertz to 2 gigahertz, so your bandwidth is 1 gigahertz, and based on that, you can calculate what is your resolution of your range. Okay? So this is the baseband signal. After we generate the baseband signal, the next thing we do is actually we up-convert this to the carrier frequency that you want to send it out. Say, for example, if you operate at X-band radar system, then you have to actually up-convert this to, say, 9 gigahertz. And then when you up-convert the signal of the LFM, it looks something like this, whereby it's actually a high frequency, have a lot of high frequency sinusoidal wave. Okay. Okay. Before we go into the synthetic virtual radar, I think I need to just to mention, okay, the radar equation. Okay, this is actually well, when we deal with radar, we need to know about the most fundamental equation, which is a radar equation. Radar equation is actually a equation to relate the receive power of the radar system to the transmit power. Okay, say for example, if we transmit a power through a gain, so the transmit power after the antenna gain, it will come to this point, and then it will propagate to send the signal to the target, and when it will send the signal to targets, pass through a range of, say, R, and this will be the propagation loss, okay, due to the sphere spreading effect. And when we reach to the targets is going to interact with the electromagnetic wave, and this is the radar cross section, which is related to the characteristic of the radar, the targets, and then a portion of the signal will be scattered and then back to the direction of the receiving antenna. So it will need to go through another round of propagation loss. Then it will hit to the receiving antenna, and this is actually the last term is about the antenna efficiency term. And once you get to this point, then it's called the received power. Okay, so a radar equation is actually required when we do the calculation for radar system design. We want to calculate the power budget. Okay? how much power required for your transmitter in order for you to operate your radar at a particular or specific distance. Okay, and also it relate to how much is your the backscattering or the RCS that you want to see. Okay, so so this is actually related to the radar design. Okay, so another term is called radar cross section. So radar cross section is a measure of how detectable an object is by the radar. Okay? So at different angle or different direction, when you look at an object, it may give you a different radar cross section. So this also it will affect how much transmit power you need in order for you to have a very good signal to noise ratio. Okay, so that is about some overview of the radar. Okay, next let us go to look at the SAR. Okay, so SAR, it stands for synthetic aperture radar. Okay, so synthetic aperture radar here means we synthesize the aperture. Aperture, this is an antenna aperture. Okay, so it's a radar system. It's an imaging radar system that we synthesize the antenna, a long antenna, by using movement of the platform. Okay, so when the platform moves, it carries the antenna, and when the antenna moves, we try to collect the signal. Okay, it's actually a range signal, but then when we have a movement, then we can collect a series of this range measurement, and through a processing step, we can actually reconstruct the signal in a two-dimensional array. So this SAR system, normally we will attribute the idea to the inventor of SAR, which is Carl Valley. He has a patent filed in the year of 1965. At that time, the technique is not called synthetic aperture radar. He called this as a Doppler radar beam sharpening technique. Okay, so the idea here is actually we try to make use of a movement of an actual antenna. Actual antenna could be a very short antenna. Okay, so based on antenna theory, if you have a very short antenna, then your beam width is actually very wide. Okay, when you have very wide beam width, basically your resolution won't be good. Okay, because this is like your 1 pixel resolution. Okay, so but then if you want to have a very sharp beam, we need to have a very long antenna. A larger size antenna sometimes is not easy for us to mount onto a platform. For example, you want to mount onto an aircraft or UAV. So a big antenna will have a difficult time, okay, for this kind of platform. So in order to solve this one, here comes the idea. Okay, so we still can have a very small antenna, but then for this antenna, we send a chip. Okay, we send a chip, the linear FM, for example, okay, at this position. Okay, and after that, we receive back, we collect and record this. This is position 1. Then after that, we go to the second position. We do the same thing. We send out the pulse, and then we record the receiver, and then we save this as, say, array position number 2. Then we continue 2, 3, 4, 5, and so on. So this platform is actually, say, moving in this direction, but then it look at the side. Okay, that's why we call it as a side-looking radar system. Okay, so the position or the direction of the propagation, direction of the flight is in this, say, we call as a long track direction Y, and then the radar is actually sent, the transmitting signal is actually sent to the direction across track direction, which is X. Okay, so therefore, when we send this, okay, at every position, we collect X direction array, and then at every azimuth direction, okay, along the flight path is actually the Y direction, you collect, okay, every array. Okay, so after that, we can have this two-dimensional array for radar image. Okay, and the main idea here is actually after we perform this data collection, we have to do some tricks in the processing to match back all the signals, okay, from the range domain. First is we have to compress the range domain to get back a very good resolution range signal. Then after that, we have to do the second time mesh filtering in the azimuth domain or the along track direction, so that we can compensate the variation in the Doppler frequency. Okay. Then the result is actually a focused radar system. Okay, before we look at the processing part, let us just look at the different mode of operation. Okay? So a straight map SAR is the most basic and also the simplest one. The flight path and the angle, the pointing angle of the radar is perpendicular. Okay? There's a right angle. So if you fly in this direction, the pointing angle is actually right angle 90 degree towards the side. Okay? And of course, it's pointing downwards. Okay? So straight map is the easiest one, simple to do in terms of the processing. The swan angle is not directly pointing 90 degree, but it's actually kind of not equal to 90. It could be less, it could be more. Okay? Spotlight mode, it always tilt the antenna so that it always look at the same spot. So that's what we call as a spotlight. Okay? You have a higher resolution because you have more this data for you to the coherent data for us to process, and therefore you can have a higher resolution image. But then it's sacrificed in terms of the area of coverage. Scan SAR, you tilt the antenna in along this along track direction. It has a wider area, but then it is less resolution. Okay, so SAR platform can be spaceborne, can be airborne, and now also ground-based. Here are some of the SAR images. Okay, so as mentioned, SAR is a high-resolution imaging radar system. It has a high range resolution because of pulse compression. This basically is the same as any other radar system. Okay? As what we mentioned earlier, whereby we use a modulation scheme, say a linear FM modulation, to achieve a very high resolution radar system in range. And the azimuth resolution, this is the one that's special for SAR. Okay? The azimuth resolution is actually we can have a very high resolution because of we synthesize a very long antenna. Okay, so let's first look at how we can improve the range resolution. Okay, so improve the range resolution is by using a pulse compression technique. So to do pulse compression, you can either do it in time domain or frequency domain. Time domain, normally we do it in hardware. Okay. Because if you want to do this in digital processing, basically you need to do convolution. So convolution in time domain is a time-consuming process. And if you want to do it in digital form, we normally will transform this to frequency domain, and then we do multiplication. So this frequency domain multiplication is equivalent to time domain convolution. Okay? So basically, the model of this signal is when you have a transmit signal, okay, you convolute the transmit signal with the match filter, and then you get a match filter output. Okay, so to implement this in frequency domain will be much easier because what we need is just to do an inverse FFT, and then we do a multiplication. We do FFT, do a multiplication with the complex conjugate of the signal. Then after that, we do inverse FFT to get back the signal in time domain. Okay, so here are some examples. Like for example, say the blue color is the transmit chirp, and then the red color is the receive chirp. Now, assuming that the target distance is at 0 distance, so you will get back the signal return at 0 time. Okay, that means immediate response. And assuming now I put a target at range equals to 100 meters, so there will be a displacement. The delay, this is a delay of the receive signal compared to the transmit signal. So we can see that there will be a time delay. Sorry, the time delay, this time delay is equivalent to the distance of the target from the transmitter. And we can always change the time to range because time is related to the range. So then we can get back the signal in range profile. Okay. say for example, if you have two targets, then it depends on the separation or the resolution that you can separate them. Okay, the resolution of the range is equals to the speed of light divided by 2b. So if we want to have a very good resolution radar, so we need to have a very good bandwidth or high bandwidth. Nowadays, if we have like 1 gigahertz bandwidth is quite a common. So 1 gigahertz bandwidth, you get about 0.5 meter resolution in range domain. Okay. This is actually one of the real radar signal we capture. Okay, in time domain, okay, you can see the signal is actually also covered by noise. Okay, and after you do the mesh filter, the filtering process, pulse compression, you will be able to see some peaks, and the peaks is actually related to strong target return. And that is this is in the range profile. So when we collected the range, then the next thing we do is actually to process it in the azimuth domain. Okay, so the azimuth resolution actually is dependent on the antenna. So as mentioned just now, the antenna resolution is actually is inversely proportional to the length of the antenna. So if you want to have a very high resolution in azimuth domain, basically we need to have a very large antenna, and this is something physically not that feasible because to mount a long antenna onto aircraft is quite challenging. So when we do a SAR processing, basically what we do is this azimuth resolution, okay, we try to do a compression, a pulse compression in azimuth domain, so that you can focus the signal and then you get a very sharp image. Okay? So the azimuth resolution for a real aperture is inversely proportional to the antenna length. But then for the synthetic aperture radar, the azimuth resolution actually is not depending, is actually is a constant, which is the antenna length divided by 2. This is the theoretical resolution. The effective one is actually a little bit more than this. It depends on the antenna design and also the system. Okay? But generally, the SAR resolution in azimuth domain is only affected by the length of the antenna. The smaller, the better in this case. Okay? So just let us do a very simple calculation. Say, for example, we have a 1 meter antenna that operates at 2 kilometer range. Okay? And then we are using a KU band signal. So by using the formula or the calculation here, yeah, these two formula, so we will see that the azimuth resolution for a real aperture radar, that means it's a conventional radar, is 35 meter, okay, at this kind of setup. But then synthetic aperture radar is actually only 0.5 meter. And good news here is that it is independent of sensing distance. Okay, so if you look at the formula here, the resolution is only dependent on the antenna length and not depending on the distance of the target. Okay? Normal radar system, it depends on the range, okay, of the targets. Okay? So here we have two dimension resolution. One is in the range domain. The range domain is dependent on the bandwidth, inversely proportional to the bandwidth. So that is something that we can control because we are the one that design the radar signal. Okay, and then in the another dimension, the y direction, the resolution is dependent only on the antenna size, and again this one is independent on the sensing distance. So this one makes the SAR is very useful and suitable for very long distance imaging. Okay, so SAR is actually widely used now, and I suppose all of us or many of you know about this one. So so it's all weather, high resolution, wide coverage, and independent on different sensor. You can have a calibrated data product, and then you can use it for many study and application. Okay, so the more complex part is actually on the image formation. Okay. The design of the SAR radar system actually not too complicated also. It's just a normal SAR or normal radar system. whereby you need to have a chip generator. Okay, of course, if you want to have a very high resolution and you want to use for interferometric application, then you need to have a very stable phase. Okay, so that is about the RF transmitter side. And then after that, you need to have a moving platform. Okay, so a moving platform, if say is a aircraft, then that is different. No, you just need to mount the antenna onto the aircraft. And of course, other challenges, it will be how are you going to collect the data? How are you going to store the data? Okay, so that we'll discuss shortly. Now let's look at the geometry of the SAR system. Say this is the aircraft that fly in this direction, and then it point the antenna towards pointing down, okay, at certain angle, and then assuming that we use a straight map move, this is a 90 degree, okay, but then this is pointing downward, okay, so we have a look angle here, okay, and then the azimuth direction is this, we call as Y, and then this is a ground range direction, we call as the X, and then we also have another dimension we call as a range dimension. But this range domain, we can actually do a projection by using the geometry to go back to the ground range, and then we will get the two-dimensional image on the ground. Okay, so basically, when we want to process the data, first is of course we need to collect the data. So say for one syntactic length, okay, we collect from this point. Okay. One syntactic length means the length that we can cover a particular target. Okay? Say, assuming we have a target at the center, and this is a point when I first can see this target. Okay? And this is actually my antenna beamwidth. The aperture can cover, say, for example, this is say 60 degree. Okay? So I can cover all the targets from here to here. So assuming there's one target here, and when I move from the first position, I already can see the targets. But these targets to the radar, the range is this range, assuming we call as a R star. Okay? So the range, the time delay related to this range is from here to here. Okay? So this is the radar that I capture. Okay? And then after that, you move to a second position, we capture again, and then we store again. And then the third position, we capture the targets and then we store. And at the center, the range is the shortest. Okay, therefore the time delay from the transmit signal to the return signal is also the shortest. Okay, after that we move on, and it will become the range from the antenna to the target will become longer and longer until this point, and after that we will not be able to see the targets anymore. Okay, so here is we call it a starting point to the end point. And if we look at the data that we have collected, okay, so this is the range, the time in range domain. Okay, you can see here is all the radar signal, every radar signal that we collect and store. And then this is actually our slow time. We call it a slow time or azimuth time. Okay, it's a step. We move from this step to another step and continue. And every step we collect a string of data. Okay, so this time is actually very short. Okay, for example, say in millisecond. Okay, we send a small chip and then we collect back this signal. And this time is actually a very long time. Right? We call it a slow time because regardless of how fast you travel, even you use say an aircraft at a speed of a few hundreds to 1,000 kilometers per hour. But then to a speed of light is still considered very slow here. Okay, so the idea of SAR processing is after you collect the data, we have to do at least 2 steps, or maybe we should call it 3 steps. Okay, first step, you have to compress the range. Okay, from this chip signal, I need to compress this become one point. Okay. And if you do this for the whole azimuth range, then you get a curve. Okay? So if we have a curve, it is not good for us to do azimuth compression. So the next thing we do is we have to straighten this curve, okay, become a straight line, and this is what we call as a range migration correction. Okay? So this only happens when the range is actually significant. Okay? For certain range, then you can actually ignore this. Okay? But assuming for general case, we have to straighten this, then we have to do a second step, which is range migration correction. Then after this, we have to do azimuth compression, and then you get a dot. Okay? And this related to one of the targets. Okay? And we do this for multiple of the different area of the image. You get the entire SAR image. Okay? Here, for the sake of completeness, I'm sorry I have to show you some equation. Okay? But I guess we can skip this also. Okay? Just for your reference. Okay? So a transmit SAR signal, okay, we can express in this form, which is a carrier frequency multiplied with the signal, okay, modulation signal. So this modulation signal in part 1 discussion, this is actually a linear chirp. Okay? Here I just make it as a general equation because for SAR system, not necessarily we use linear chirp. We can use other different types of signal modulation scheme. Okay? But here, this is a transmit signal. Then the receive signal is actually a delay of this, which is you have a time delay. Okay, that means the function of time minus a delay due to the reflected signal from the targets. Okay, so it's a series of delays, okay, collected from the targets. And after we do the demodulation, that means we already do the down conversion. So the carrier frequency will be cancelled off, but then the delay will still remain here. Okay? So this delay is related to the round trip delay from the target to the scatterer. And the range, we can actually use approximation to say this is actually, although it's a square root, why square root is because of the, if you look at here, for every range, okay, is actually a function of this slant range, this R, and also the distance, the displacement here, okay, to the center point of your azimuth domain. Okay. So it's actually using a square root of 2 terms, but this is difficult when we do the signal processing. So normally we will try to approximate this into a function, okay, a constant multiplied with a time square, okay, and this is possible because the range normally is very big or very large compared to the time delay. Okay, so by having this, okay, we actually can get back a equation related to the receive signal. Okay, so this receive signal basically it means the raw data that we receive. And then, so the signal processing basically is we try to operate on this equation, okay? We operate on this equation so that we get back a 2-dimensional image, okay? So if you look at this term, basically there are 2 terms, there are 3 terms here. So the first term here is related to the frequency modulation scheme of the transmitter. So this one we can reconstruct by using a pulse compression technique. This term is related to the range of the targets. So this one we can do remove this by using say a range migration and also some other more precise techniques. Okay, I'm not going to cover all this here. Okay, the third one is related to the chirp in azimuth domain. So we can try to reconstruct this one by using an azimuth domain mesh filtering. So basically, a typical SAR processing step, we do the range compression in frequency domain. Okay, this is easiest to do because if we want to use time domain, we have to do convolution. Okay? So this is the range domain compression. Then after that, we convert to azimuth domain. We do the range migration before we do the azimuth compression. Okay, and then after that is a compressed data, which is a 2-dimensional SAR image. Okay, so in terms of the algorithms, if you want to relate that to the equation, So basically, we multiply with a complex conjugate of our transmit signal waveform, okay, during this range compression process. After that, we do another also, azimuth compression is also, in a way, is a mesh filtering in azimuth direction, okay, by multiplying a term which is actually the term we derive here, okay. So based on that, we get two-dimensional SAR image. So very important is actually we need to have the reference function, okay. So every SAR system, they have a bit unique reference function, depends on the design of the system. So a typical linear chirp reference function is like this, and then the azimuth reference function is something like this, okay. So that you can generate by using the software. Here are some simulation. Say we only have a single point target, okay. So the return signal, you look at the fast time and the slow time, and if we just purely display, we get a signal like this, okay. Then after that, we do a range compression. After range compression, basically we will do it in this range domain. You get a line, okay. Instead of one whole broadened kind of image, then we get one line. And then after that, we straighten this in the range migration process, or you can actually combine that with azimuth compression by using some advanced techniques. Okay, so basically, after we combine, then we get a sharp focus image. There are different algorithms to process SAR. Okay, the one that I showed you just now is called a range Doppler algorithm. Okay. There are other algorithms, for example, chirp scaling, omega k, and so on. Okay? So that I think we won't go through details. The last part I want to share with you is on some design ideas. Okay, so basically, when we have a SAR, what do we want from the SAR? Okay, the advantage of SAR is we have an image, two-dimensional image, and every pixel actually carry the amplitude and also the phase information. Okay? So the amplitude or the power information is related to the backscattering coefficient. Okay? So if you still remember just now when we discussed on the radar equation, so the radar equation, what we receive is the power, the received power, and the received power is related to the backscattering coefficient or the radar cross-section. Okay? So every pixel of the SAR image, it contains a function of this target characteristic. So this is actually a very useful information for us to do classification, for example. And there's another information inside the SAR signal is phase information. Okay? So the phase information is important if, say, we want to do polarimetric SAR or interferometric SAR, where we need to get the phase information and we have to operate on the phase information for us to retrieve the phase related parameters. Okay, for example, the time series or temporal change detection, or you want to do the digital elevation model from the SAR interferometric SAR system. Okay, then the phase is actually important. Okay, but for normal SAR system, basically after we get the SAR 2D image, we square it, and then we get the backscattering coefficient. Okay? So when we design the SAR system, basically it consists of few parts. Okay? One is called the subsystem. Subsystem involves antenna, design, the RF electronics, digital electronics, and also timing and control system. Then the platform, okay, and also the data acquisition system. Okay, how we capture data, how we store data. One of the challenges here is actually on the storage, okay? Because say imagine we have a very high resolution, high bandwidth data. So typically one scan you may have like hundreds of gigabytes of data. So how are we going to save this one at a very fast speed? Okay? Imagine the platform is actually keep moving. Okay? And after that, there's another system which is a processor. Okay. So when a typical SAR system design, we first, of course, we need to know, okay, what is the application of the SAR? Okay, you want to apply for forest forest monitoring, urban land use classification, or say this oil palm plantation monitoring or others. Okay, so depends on the user requirement. Then we have to design the system accordingly. Okay, first is we have to select the frequency, and then the resolution. Based on the resolution, we have to select what type of modulation scheme, and whether we need a polarization, a full polarization. You need more antennas, you need more processor, or you want like interferometric SAR kind of system. Then based on the targets, we try to calculate what is the dynamic range required. Okay, so this dynamic range will determine what is the transmit power we need. Okay, and also what type of the power amplifier and also the low noise amplifier and so on that we require. Okay, operating platform, are we going to put this onto a UAV or airborne or spaceborne? Okay, that will also relate to the payload that we can allow. Okay, a small UAV, typically now you may only can have say 1 kilogram kind of payload, so everything has to be very small. Resolution, what type of resolution we are talking about, and then what are the incident angle or swap width we need, and so on. So antenna is another big topic, okay, in SAR system design. Okay? And this antenna also related to how you want to mount this into the platform. Okay, so example, say a wavelength, normally we select in centimeter range, polarization, pulse width, bandwidth, and so on. So this is one example. Say we developed one airborne SAR system back in 2009. Okay, so that time we used straight mode C-band frequency. The bandwidth is just 20 megahertz because we fly at a very high altitude at about I think it's 10 km. Okay, and we just want to do the Earth environment monitoring, okay, terrain mapping, and also classification. We use at that time the recorder is just about 100 gigabyte, okay, for one flight. We fly for 5 hours, okay, and then the resolution is about 7.5 meter, okay. The platform height is 7.5 kilometer, okay. This is one of the typical system block diagram, whereby you need to have the oscillator, the frequency modulation scheme there to control the jerk signal, go through the high power amplifier, send out through the antenna, then come back. We have the low noise amplifier, go through a bandpass filter, and go through all these intermediate frequency and also amplification. Then you do your A to D, collect the data, and then store it, and let the ground system to process. Okay? Antenna, normally we prefer to have a 2 antenna system rather than single antenna system. Okay? The single antenna system, your isolation of your port must be very good. This is another radar system, just to share with you. It's a ground-based radar system that we developed recently. Operate at KU band, sweep bandwidth is 300 to 1 gigahertz. Okay, the resolution at 1 kilometer is about 0.5 meter. Okay, it's used for temporal change detection, so it do the time series interferometric scanning, okay? And it used for example, landslide monitoring. Okay, so the trend of SAR development, I will say now we go for very high resolution SAR, and then because of now it's more flexible. If we have we have a micro satellite system and also nano satellite, okay, and also we have low altitude this UAV. So miniature SAR is one of the current trend of SAR design. We want to make the SAR smaller, lighter, and also have a higher resolution so that we can have a very real-time operation. Okay? It's just like camera. I will foresee that in the very near future we will have SAR as accessories, okay? Just like an accessory for your handphone. Okay, we have a SAR system for this kind of object detection, and also some of these are several applications. Okay, for by using multi-frequency and also 3D imaging. Okay. I think I will stop here because we need to spare some time for Q&A also. Prof. Chan, over to you.
Thank you, Professor Koo, for your very wonderful speech today. And I see not only you introduced the fundamental series of SAR, but also really introduce some practical SAR system in this speech. Yeah, we appreciate your talk today. And right now we only have 4 minutes. Any
Sorry.
no, it's okay. Any questions?
Hi, Professor. I have one question that why the SAR system is located at the side of the airborne or a satellite craft?
Why the SAR is located at the
side of the airborne?
Oh, okay. Why is it side looking? Is it?
Yeah.
Okay. So your question is why this SAR system is always looking at the side, not looking front, right? So because we need to have a two-dimensional image, right? So if you're looking at the side, then you just imagine that you fly. Okay, this is a flight path. You look at the side. Okay, it's like a scanning. Okay, I have one range. When I move the platform, I look at the side. When I move, I will be able to scan and then get the 2D image. Okay. If I look at front, they also have some SAR system is actually a front looking. Okay? The process is a bit complex. Okay? Normally, you just imagine it's a scanning mechanism. Okay? You scan like that, then you get your 2D image. That's why SAR system is side looking, because we need to produce a 2D image.
Okay. Thank you, Professor.
We got time for one more question. Any questions? Yes, Professor Muhai.
Hello.
Yes.
Yeah.
Please.
Thank you very much for the interesting talk. Actually, my question is regarding the SAR limitations. You have mentioned some of the SAR advantages, such as real time and low cost. But I was wondering, what are the limitations of SAR? Thank you.
Okay. Currently, if you talk about SAR system, we can always compare with optical system for remote sensing application. So if you compare SAR and optical system, SAR system is more expensive. Okay, in terms of price and also it consumes high power. In terms of operation wise, it's more challenging. Okay, like for example, say you want to design a payload, a spaceborne SAR. You have to consider about the power, how much power you have to carry, because SAR, it requires Voon transmitter. So the limitation of SAR is actually mostly on the power consumption. If you want to go for, say, airborne system, UAV flight, okay, using SAR compared to optical camera, maybe you can use the same battery, you can operate for 1 hour, 2 hours. But then using the same battery, maybe you just operate for a few minutes. Then you have to recharge the battery. Okay? Another thing is SAR system is more bulky, bigger. That's why now, because of the advancement in the electronics technology, we try to shrink this down so that the SAR is kind of more closer comparable to the optical imaging system. And SAR system, another challenging thing is about the processing. Very complex processing. You need a good processing, a good processor for you to do a real-time processing. So all these things make up SAR is actually a more difficult or more complex system compared to other sensing solution that we have now.
Okay, thank you.
Thank you.
However, we're really running out of time. And once again, let's thank you, Professor Koo, for your very, very outstanding speech today. And finally, let us give Professor Koo a big hand again, okay? And thank you for his talk today.
Thank you for your time.
And in case if you got any other question, that you are encouraged to write an email to Professor Koo. You can find his email address in his website. Okay. So thank you again for all Professor Koo and all of you to attend today's seminar. And I hope we also have a 4 more seminar for this series, and then you are welcome to join later. Thank you.
Thank you, Prof. Chan, for your kind arrangement. Thank you to all.
Thank you. Okay.
Yeah. Bye bye.
See you all later.